And we'll see how this goes. The other thing I wanted to do was share my screen. Okay. So if everything's working properly, I'm sharing my screen with you. And this is called Bertrand Part 2. And it's called Part 2 because last Saturday at the same time, we did Bertrand Part 1. And what is Bertrand? Well, the easiest way to answer that is to go look at the code because we left ourselves a comment in the code. But let me just outline the plan today. This may not take a full hour. Our goal is to remember or review what the Bertrand program is supposed to do, to see how far we've gotten so far, to remember some of the basics for how modulo works and our rationale for the logic in the isIt_prime function, and then to continue on and write some new code that actually finishes the problem of being able to test Bertrand's postulate. So that's the plan for today. Okay, so I'm going to go up to the very first line of code up here, and I'm going to read what it says to me. It says, Bertrand has said it. I'll say it again. There's always a prime between n and 2n. And that little poem says that if you pick an integer n, let's say 2 or bigger, let's say, for example, 7, and then you calculate 2n, well, 2 times 7 is 14, and you start counting the numbers in between 7 and 14, so in between means 8, 9, 10, 11, 12, and 13, somewhere in there you're going to find a prime number. That's what Bertrand said, and we're going to see if we can write a Python program that either supports that idea or finds a counterexample. And by a counterexample, we mean you could try and find a number n where there are no primes in between n and 2n. Okay, but really the goal here is to start learning to think in terms of how Python works or how a computer program works, how it executes from the top to the bottom, how we put values that we're interested in referring to inside of a variable, how let's see, we think about the flow of logic and how things like not in front of a term can change its logical value. So you can have an expression in a Python program and look at it and say, this is true or this is false. But then if you put a not in front of that, it flips it to be false or true. So let's review the very first line of code, which is this one here from random import randint. This is called what is called an import statement. And what we're doing is we're saying, go and make all the randint stuff available from the random library. So that means we can generate random numbers, but we're not actually going to use that in our Bertrand program. We used it for the Meteor code, but I have commented out the Meteor code. So when I paste this code back into Slack, you could uncomment the Meteor code if you wanted to run that. Then we import time, and we're going to use that. Actually, we're going to use that for making little delays, like little sleeping delays. And then there's the import math, and that package or that library we're going to use for the square root. And we imported sys for the purpose of being able to stop the program whenever we want to by using sys.exit. Okay, this is all kind of a side note. Let's get into how things work in our Bertrand program. So first of all, it talks about n and 2n. So let's consider n and 2n for a moment. Here I have a variable declared. It's called n. That n is its identifier. It has a type, which is integer. How do I know? Because 12 doesn't have a decimal point after it. And so 12 is going to be an integer. And then it has a value. And what's the value of n? The value of n is 12. And then we have 2n, which is a new variable, which is defined in terms of n. So it's 2 times n. So we expect that to be 24. So if we run this program and it prints n and 2n, we expect to see 12 and 24. And then it will print n, and then there's this percent sign, which we pronounce modulo 7. And that is what is the remainder after you divide n by 7. And 12 divided by 7 is 1 with the remainder of 5. So now we can predict what we should see in our output screen when we run this program. And sure enough, we see 12 and then 24, And then when the next line, we see 5. So everything's working as expected, although this little error message just means that it ran into my little exit message here, and that's what's happening. So I'm going to take the exit message and move it down a little further. Oh, wait a sec. It says compare. So there's a comment here that says compare. And now let's take this n modulo 7 print statement and break it into 2 pieces. Okay, so I said n modulo 7, and that is a new variable. That's its identifier. And I'm going to set that equal to n modulo 7. Okay, and then I'm going to print n modulo 7. So there's nothing tricky here. This is just 12 modulo 7. It should print 5 a second time. So let's run that. And sure enough, it prints 5 a second time. So what's the difference between the first time we did this, up here, print n modulo 7, and the second time we did it, which is n modulo 7 equals n modulo 7, print n modulo 7. Well, the second time, it took us 2 lines of code to get the same thing printed on the screen. The first time, we actually combined 2 things into 1. So we were being rather tricky. By putting n modulo 7 in here, we told the Python interpreter, go figure out what's inside the parentheses and then print it. But we did that in a sort of simple way that used only 1 line of code. But the way that we think might be, well, let's go set a new variable equal to this result, and then we'll print that variable. So both of those methods are equivalent to one another with one difference. That is, when we get down to here, when we fall through this print statement and continue on with our program, there's going to be a variable that knows what n modulo 7 is. Whereas up here, when we just did the print statement, Python is going to forget all about what n modulo 7 is, okay? So whenever you want to retain a value, it's useful to think in terms of, oh, I better put this in a variable or a little bucket that's going to keep that value around for a while. Okay, so we're going to take this 6.exit away, and then we're going to review our logic statements here. Boop. Okay, so we use logic in Python programs and computer programs in general to control how the program moves from one idea to another. Now, we're going to be checking for prime numbers in a second, so we want to make sure we remember how the logic works. Remember that in Python, any integer that's not 0 is considered to be true, and any integer that is 0, that is to say 0, is considered to be false. And then when we put a not in front of something, that changes it from being false to true, or it changes it from being true to false. So not is the negation logical operator. What's going to happen in this first line of code? If n modulo 5, print n is not divisible by 5. What that means is if n modulo 5 has a non-zero remainder, which of course we know it is because 12 divided by 5 is going to be 2 with a remainder of 2, then it's going to print 12 is not divisible by 5. And then it's going to check 6. It's going to say if n modulo 6, well, what is n modulo 6? N is 12, so 12 divided by 6 is 2 with the remainder of 0. So this is actually going to be 0, which is to say it's going to be false. But look, we put a not in front of it, so that's going to make it true. So now we say, if true, print 12 is divisible by 6. Okay, so we expect this to work properly. Then we have if 3, well, 3 is true, so it's going to print 3 is true. Then we have if 0, print 0 is true, but 0 is false, so we don't expect this print statement to run. That's the consequence of having an if statement, is if your thing that you're evaluating is false, then what you tell it to do next won't happen. It'll skip over that. If we want it to be proper, we would actually indent this as a block of code below. So everything in that block of code will be skipped if 0 is false, which it is. Okay. Okay, if not 0, print not 0 is true, so 0 must be false. Okay, so is this going to work? Well, 0 is false, not 0 is true. Print, so this means that this print statement is going to run. And finally, we have if not 3, print 3 must be false. Okay, let's make sure that all these things do what they expect, or what's expected. Okay, so it says There's our initial numbers. 12 is not divisible by 5. 12 is divisible by 6. 3 is true. Not 0 is true, so 0 must be false. And it did not print 3 must be false. Now, here's a question for you. What if I say if not 3? Okay, let's work backwards. So 3 is not 0, so 3 is true. But not 3 is false. But you see how it works? Not 3 is true, because not 3 is false. So right now, if not 3 is true, then not 3 is false. And not 3 is true. And not 3 is false. And not 3 is true. And not 3 must be false. So it's not going to print this because at the very end it's going to be false. And sure enough, it did not print this. But if we put in one more not, now it should be true again. And it should say 3 must be false. How about we just change this to say, well, let's just run it. Whoop. 3 must be false. And here we've made a mistake because 3 is true. So we'll say something more accurate. The if is true. Let me run that. It says the if is true. Okay, that's enough of a review. Now let's take a look at our is it prime function. You may recall that the goal of our prime function, is it prime, is to take a number q and determine whether or not that's a prime. And if it is a prime, it returns true. So it's using the logic that we just practiced using. We're going to detect a composite number. That means a number that has factors other than 1 in itself by checking all possibilities that we need to check. The logic goes like this. If you have a composite number and you divide it by some factor and the factor divides into it, then the modulo of that factor is 0, which is false. So for example, 12 modulo 2 is 0. That's false. But we're trying to detect when that happens, so we use not modulo, which is going to be true. And when that happens, when we find something that divides evenly into our q, then we want to report back this number is not a prime. Since our function is called is it prime, we want to report back false. And that's what leads to this mysterious line of code inside of our while loop. If not q modulo possible factor, return false. Now, if this is confusing to you, you may have not been on the call last week, or it may be that I'm going too fast. And at this point, it would be great if this is confusing or it doesn't make sense for you to hop on the microphone and let me know that that's the case. Otherwise, I'm going to continue with my review here. Okay, so is it prime has a documentation string that tells us what the method does. And then it says, I'm going to assert that the number I'm supposed to look at is bigger than 0. Because if it's not, that's not what this program is written for. So it's a little safety check. Now, if q, the number that's supposed to be tested, is 1, we return false because 1 is not prime. If it's 2 or 3, we return true because 2 and 3 are both prime. If it's an even number, if q is even, then when you divide q by 2, you're going to have a remainder of 0. And not 0 is true, and therefore it's going to return false. Why false? Because the question is it prime? And the answer is no, because it's divisible by 2, so return false. Small factor is 3, and now we're going to start counting up 3, 5, 7, etc. And we're going to check all those odd numbers to see if they divide into q. But we'd only have to go as high as math.square root of q, because any number bigger than that that divides into q is going to be multiplied by something less than the square root. So it's that balancing act. For example, 35 is divisible by 7, but the square root of 35 is a little bit less than 6. So we only have to check up to 6 because we would find 5, and 7 times 5 is equal to 35. So 5 is as high as we need to check. We don't need to check 7. Okay. That's how our prime factor function works. Just to review it one time, we'll make sure that it still works properly. Print, is it prime of 1,987, 2? And I happen to choose a number that's divisible by 3. So let's find out what happens when we run. It should not be prime. Oh, I forgot to get rid of my exit function, my exit call. Okay, so let's run this again. So we're going to print at the very end of the program, is it prime? This is not a prime number because it's divisible by 2, for example. Well, let's just make it, let's see. I'm going to make this a little bit bigger. Yeah. So if it's prime, it'll print true, and if it's not prime, it'll print false. Oh, it's very important for me to put this, see what I did there? This is a good example of a mistake. So when I created this test statement, this print statement, it was indented here, and therefore it didn't run. So now I'm going to put it back at the edge where it's going to run for sure. And it says false. Okay, so this number, 19,881, is not prime, and so on. Okay, so here's our last task for the day, is to actually check Bertrand. And the way I'm going to do that is I'm going to talk about the logic of building yet another function. So just as in creating this function up here, is it prime? I'm going to imagine that there's a function that returns true or false, and it's going to be called check Bertrand. So I'm going to say def check Bertrand. And so this is, and it's going to be past some number n, because remember, it's between n and 2n. So the way to think about writing a Python program is, once you have an idea of something you need to do, and you have a nice, like you can sort of hold it in your hand or imagine that it does something very important to the program, then you can say, okay, it's time to write a method. It's time to write a function. And you start with this def term. And you write def, and then you make up a name for what it is that has something to do with what it does. And then you decide, what does it need to be told? In our case, we need to know what n is so we can check between n and 2n. And then you can go off and you can do the logic inside the function. So since our function is called check Bertrand, let's have it return a variable called found a prime. Okay, so all we have to do is set found a prime. And now we'll say that there's some code here that says set up found a prime, then check n plus 1, n plus 2, n plus 3, ... all the way up to 2n minus 1. Are any of them prime? And then return found a prime, okay? So I've written this in English because sometimes it helps me to think about my code if I write it in English. And now I'm going to translate set up found a prime. So found a prime is a variable. And I'm going to say, well, we haven't started counting yet, so I'm going to set this equal to false. So found a prime is false. And now I made check n plus 1, etc. All of those things, all this line of text, I put this in a comment so it won't actually run. And now my program is going to return found a prime. So when I run this program, it's not going to actually execute check Bertrand. It's going to remember that there is a function called check Bertrand, and it's going to wait for me to actually call it. So let's call it down here. Result equals check Bertrand of 7. print result. Okay. So now what happens? The program runs. It does some print statements at the top that we don't care about anymore. It says, okay, there's a function called isItPrime. I'll remember that, but I'm not actually going to do anything here. I'm just going to remember that there's a function called isItPrime. Then there's a function called checkBertrand. I'm not going to do anything here. I'm just going to remember that this exists. And then, we got a little feedback. And then we're going to say result equals checkBertrand of 7. So we're going to actually check this where n equals 7, and then we're going to print the result. So what happens when we run checkBertrand? Well, checkBertrand starts running. It's been passed a number n, which is 7. It's going to say found a prime equals false. Then it's not going to do anything for a while, and then it's going to return found a prime. So it's going to return found a prime, which is false. So it's going to return false. Now, there's supposed to be a prime between 7 and 14, so it's giving me the wrong answer, but that's okay because we are not done yet. So I'm just going to run this and make sure that it happens. Okay, so that happens exactly as we hoped, but I'm going to make this print statement a little bit more clear. Like that. I'm also going to go up here and I'm going to print some blank lines. This is a blank line character. I'll print 3 of them so that it's clear what's happening before our test and afterwards. Okay, where's that print statement coming from? Oh, we don't need this anymore. Okay, so the program ran and it printed false right above Bertrand result is false, and that false was from our previous test, so I got rid of that line of code, and now it just prints our Bertrand result here and very nicely. Okay, so we're done for the day, except we forgot one thing. We actually need to write the part of this program that does what we came here to do, which is to check all the numbers n+1, n+2, n+3, and so on, to see if any of them are prime. Well, we already have a function up above that checks if a number is prime, right? But what we need to do is we need to start checking these n+1, n+2, and this is what computer programs are very good at, is doing loops. So I'm going to create a loop. This may be familiar to you, it may not, but the nice thing is that you have a wonderful book and you have other resources with the club to learn about how to create loops. So I'm going to, with very little explanation, unless you have questions, create a loop that's going to count from n+1 to 2n - 1. And the way I'm going to do that is I'm going to say for, okay, and then between numbers are n+1 and n+2. I'll call it between number in range n+1, comma 2 times n. And this is not the end of our program, but it's a good start for the next phase of what we want to figure out. So I'm going to write the comment up here, check n+1, n+2, etc., up to 2 times n - 1. So this range is something called an enumerable. It creates a series of numbers that start here at n+1 and goes all the way up to 2 times n, but it doesn't do that last one. So it only goes up to 2 times n - 1. And what happens is there's a variable called between number that's going to take on each of those values as we count upwards. So far so good. Now we have between number, and the question is between number a prime? So let's find out. Is it prime between number? Okay, so what does this do? Is it prime means go find the function is it prime and run it now, but it's going to be expecting a number. And up here, when we wrote that program, where did our function go? Here it is it prime expects a number q. But down here, we're saying, is it prime? And we're not giving it q, we're giving it between number. Okay, so this is a good example of communication between two parts of a Python program. This part of the program is used to call or execute or run or start up the isItPrime function, and we're handing it a value that's in the between number variable. But the function itself up here doesn't need to know what we called the variable, it just needs to know what the value is. So the value is what gets sent up. So suppose that we're doing this with n equals 7. Then when we run this program and start running check Bertrand of 7, then when we do this for between number, it's going to start with n plus 1, which is 7 plus 1, which is 8. So it's going to say, is it prime? And then between number is going to have a value of 8. So it's going to send the number 8 to the isItPrime function. And isItPrime is going to run, and it's going to say, okay, I've been handed q, and q has a value of 8. So it uses a different name for q, for the number 8. And is q1? No. Is q2? No. Is q3? No. So none of these is going to happen, these if statements. But down here, when we get to if not q modulo 2, return false. And that says if q is even, then send back false. And q is 8, so it's even. So this is going to return false. So in other words, when our check Bertrand function is running and between number has a value of 8, isItPrime is going to return false because 8 is not prime. Okay? So we'll say, let's see, how do we want to do this? Let's say if isItPrime of between number. So in other words, if we get a true back, then we'll say, aha, found a prime equals true. Now I'm going to do something profoundly valuable, useful, which is I'm going to say, once I find a prime number, then Bertrand's postulate has been proven to be true. So let's do this for n equals 7. So n equals 7, great. We send 7 up to isItPrime. No, sorry, we don't send 7, we send 8 because we started n plus 1. So isItPrime, and then between number is 8, and that comes back false because 8 is not prime. So this is not going to run. Okay, and so then it comes back around on the loop and it says, well, what comes after 8? 9. So is it prime of 9? But 9 is 3 times 3, so that's going to come back false also. So this still isn't going to run. And when we send it 10, 10 is going to come back false because 10 is a composite. It's 2 times 5. So this is still not going to run. So this if statement has not run yet because we've checked 8, 9, and 10. But when it checks 11, is it prime of 11 is going to come back true. So this if statement is going to evaluate as true, and it's going to run this line of code, and it's going to set found a prime to true. Okay, so now we continue counting up the rest of the numbers, and at the end of all that, when this for loop finishes checking all the numbers, if somewhere in there we found a prime, then found a prime is going to be true, and we're going to return that value. Okay, so let's do it. We'll say result equals check Bertrand of 7, and then we'll get the result. So I'm going to run the program. And now it says, instead of false, it says Bertrand result is true. Okay, so this is essentially everything that we planned to do is now working. We now have a program that checks a number like 7. Let's try a different number like 19. And it goes between 19 and 2 times 19. So it starts at 20 and goes all the way up to 37. And it checks all those numbers and it looks for a prime. That's what check Bertrand does. And if a prime number is found, then it will come back and say, yep, Bertrand was correct. There was a prime found. But there's 2 aspects of this program that we can improve. The first one is once we find a prime, we don't need to keep looking for more primes, right? One prime is enough to prove Bertrand right. So we can tell the program, okay, now that you're here and you found a prime, stop going through these numbers and checking other numbers. We don't need you to do that. And the way to do that is called a break statement. So if I put break here, it will not only say found a prime is true, but it will say also, I'm going to fall out of whatever loop I'm inside of. So the between number loop will stop running and it'll just go here. Okay, so let's make sure that this still runs. We'll check Bertrand of 19, run. And it says Bertrand result is true. Okay, so Bertrand being true means that there was a prime found between 19 and 2 times 19. Okay, let's try a really big number, 190. Bertrand result is true. How about 1900? Bertrand result is true. Okay, so Bertrand seems to be holding up okay. There's one other thing that I'd like to do though, which is when I find a prime, I'd like to know what that prime number is. Well, when in our program logic can we do that? Let's suppose that we run the program by saying result equals check Bertrand of 1900. Let's think about what happens in the program flow. We get down here, so we pass by these two initial functions, is it prime and check Bertrand. Nothing actually runs. The program just, the Python interpreter just remembers that there are these functions there waiting to be called. Then it gets down here and it says, oh, here's a line of code that I can run. Result equals check Bertrand of 1900. Okay, I know how to do that. There's a function up above called check Bertrand. So it goes up here, brings along the value 1900 and sets Q equal to 1900 and lets, oops, I made a mistake. It sets N equal to 1900 and it runs this code. And in this code, it starts counting 1901, 1902, 1903, looking for a prime number. But every time it does that, it calls is it prime. So is it prime is sort of living inside of this loop, and is it prime has its own loop, this while loop here. And so that counts all the possible factors of Q, which should start off being 1901. Okay, so result equals check Bertrand runs check Bertrand, which then runs is it prime a whole bunch of times. And at some point, if it finds that prime number, then this block of code right here is going to run because it found a prime. So let's have this block of code, since we now know that there's a prime number and we're about to fall out of the loop. Let's print the prime number that we just found. Check Bertrand found a prime equal to, comma. Now what do I write here? I'll pause for a moment while you think about this. Okay, so a print statement is going to print this string verbatim because it's a string, it's in quotes. And then it's going to make a little space and then it's going to print whatever we put here. So we could put another string, but that's not the way we want this to work. We want it to be flexible and to print out the prime number. Well, the prime number that it just found is the Q value that we passed to is it prime, which is called between number. So here we write between number. And now we're all set. So not only will this program run and check between n and 2n, but it will also tell us when it finds a prime what that prime number is. So let's find out. Okay, check Bertrand found a prime equals 1901, and Bertrand result is true. So let's make our 1900 number be a little bit bigger. We'll make it 19,000, and now we'll run that program again. Check Bertrand found a prime, 19,001. Okay, how about if we make it 190,000? Okay, so 190,000, our program had to go all the way up to 190,027. So it had to check 27 numbers before it found a prime, but it did find a prime and Bertrand is still okay. Shall we make this number bigger still? Let's make it 1,900,000. Yep, 1,900,009 is a prime. Okay, how about 1,900,000,000? Yep, 1,900,000,043 is a prime. So our Bertrand result is still true. Okay. So this is pretty much everything that we wanted to do. So the last thing I'll leave you with is a challenge, which is a challenge to write a Fibonacci sequence program. So this program writes the Fibonacci sequence, and I'm going to create some notes right down here for you, and I will include these notes when I paste this program into Slack. So what is the Fibonacci sequence? I imagine that you know, but just to remind you, the Fibonacci sequence is a sequence of positive integers. And the very first one, some people think the very first one is 1, but I like to say the very first one is 0. So I'm writing a 0 down on the screen. And then the very second one is 1. And after we have those two numbers, everything else is calculated. So we start with those 0 and 1, and then we calculate. And what's the next number? The next number is 1. And what's the next number after that? I wish I knew how to get my sharing. What happens if I do that? No, I don't see the chat. I'm sorry. If you guys are writing into the chat, I'm not seeing it because I have not mastered how to bring up chat while I'm okay. Well, I'll assume that you're following along and probably guessing ahead. The next number is, of course, 2. The number after that is, of course, 3. The number after that is, of course, 5. And after that, it's 8. And then 13. So if this looks at all mysterious to you, all we're doing is taking two numbers and adding them together to get the next number. And 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8, and 5 plus 8 is 13, and so on. So this would be the output of a Fibonacci number program. Okay, so the first question for you is, can I write a Fibonacci program that prints the first 5 or 10, let's make it at least 30 Fibonacci numbers, and then stops? So that's the first challenge, is to write a bunch of Fibonacci numbers and then stop. It will use the idea of a loop. You can use a while, you can use a for loop, and it will allow you to practice working with variables and working with the logic of creating a Python program. However, there is a bonus challenge, which is to print 2 numbers on each line. The first number is the Fibonacci number. Uh-oh. Oh, that's okay. Okay, so I had a little glitch on REPL.it. So the bonus challenge is to print 2 numbers. First number is the Fibonacci number. Okay, and then a comma, then this Fibonacci number divided by previous Fibonacci number. So for example, if we're starting off 0, whoopsies, 0, 1, 1, 2, 3, 5, 8, then the very first thing we're going to print here is just print 0 here. Okay, and then the second time we're going to do print 1 divided by 0. This may cause a problem because 1 divided by 0 is undefined. And then we get down to here, third line, and we say print 1 divided by 1, which is going to be 1. Okay, so the idea then is to print 0 and maybe just print nothing, and then 1 and maybe just don't print anything. But then you get down to the third number and now it starts to make sense. 1, comma, 1.0. And then the next one is going to be 2, comma, and then 2 divided by 1 is 2. And then 3, comma, 3 divided by 2 is 1.5, and so on. So this challenge is really about doing the Fibonacci numbers, but then also calculating these fractions, 1 divided by 1, and so on, the Fibonacci number divided by the previous one. Okay, so that's my Fibonacci challenge. If you're interested in trying this out on your own with nobody narrating, so good luck. And I'll stop everything there by saying thank you so much for coming here on a Saturday morning. And we'll hope to see you in Slack and at the club. And please do send me any questions you have. And yeah, that's it. Thank you again.
Bye.